Hey everyone, welcome back to my channel. So I've been working on a fun little project lately and I'm pretty excited to show you. Check this out. A real-time Dice Pip Counter running entirely on this ESP32-S3. No fancy cloud servers, no phone apps, and no, not even a heavy AI model. Just a ESP32-S3, a camera module, and some classic, beautiful computer vision all written in pure C++. And the best part, I didn't have to reinvent the wheel. I'm using the OpenCV component for the ESP32. Because it's an integrated component, it was incredibly easy to plug in and start using actual powerful OpenCV functions right out of the box. Let me show you how this thing actually works. Okay, so step 0, the live camera feed. What you're seeing right now is the raw video coming straight from this little OV5640 camera, pushing a 480 by 320 resolution in RGB 565 format. Since the display is landscape, we have to rotate and crop the frame on the fly to make it fit. Now, when I say near real time, remember this is a cheap ESP32, not a massive NVIDIA GPU. A very single frame has to be copied out of PSRAM, rotated 90 degrees pixel by pixel in software, and then pushed over SPI to the display. Because of that heavy workload, we are getting around 10 to 15 frames per second. It's not outstanding, but it works fine for simple projects. Welcome to step 1, Grayscale. The camera sends colors in RGB 565 format, which means 16 bits of color data packed together. But color is actually pretty distracting and mathematically expensive for tiny chip to process. We need to simplify things. So our first job is to turn every pixel into a simple brightness value. As you can see on the screen, the dice faces are now bright white, the background is a neutral gray, and those little dots, the pips, are dark. Okay, let's tap again. Now we are getting to the magic. Step 2, Otsu thresholding. The goal here is simple. Turn the image into just pure black and pure white, no in between. Normally you might just say, hey, if a pixel is darker than a certain number, make it black. But the moment the sun goes down or your room lighting changes, a fixed number completely breaks your project. That's why we use Otsu's method. Instead of a guessing game, Otsu looks at the histogram of the whole image, basically the map of all light and dark pixels, and mathematically calculates the perfect cutoff point for that exact frame. It adapts to the writing automatically. Once we find that perfect line, we invert the result. We flip black to white and white to black. You can see them clearly on the screen now, but you'll also notice some random white noise around the edges from shadows and textures. Let's clean that up. Tap again. Alright, step 3, Morphological opening. Fancy name but super satisfying concept. From the previous step, Otsu did a fantastic job and the image actually looks pretty clean already. But in computer vision, we cannot just rely on luck. To make the dots mathematically perfect, we use an operation called opening, which is a two-step combo, first on illusion, then dilation using a tiny 3x3 pixel shape. What this does is smoothly shape off any rough edges and ensure every single pip is perfectly isolated, a distinct circle. Look at the screen now, those white circles are absolutely razor shaped and ready for the final step. One last step. And here's the grand finale, step 4, the final count. This is where our clean white dot finally turns into a real answer. OpenCV makes this part incredibly easy. First, the code finds all the separate white shapes and runs them through a quick filter. It checks the size and ensures they are actually a round circle, not long weird shadows. If a block passes the test, it's officially marked as a true pip. Next, the system automatically looks at the distance between the dots. Since pips on the same die are close together, the code instantly groups them into clusters. Finally, we just sum them up. Look at the screen right now. Red circles are perfectly looking onto every single pip. Green boxes are framing each individual die cluster, and the final score pops right up. That's the basic breakdown of how this little guy thinks. But if you want to see the actual magic, all the details and code are waiting for you on my GitHub. Before we wrap up, I've gotta show you the hardware that makes all this possible because it is a pretty good setup. This right here is an ESP32-S3 development board that comes with a built-in 2-inch display, but the best part, it allows you to directly attach a OV5640 camera right to it. It's honestly the perfect all-in-one combo for any project that needs both a screen and a camera, and it's easily one of my favorite boards to play with. But the real MVP is this 3D printed frame I designed. See these holes on the 4 pillars? Those are for attaching LEDs later. In computer vision, less shadows means better results. To get the best accuracy, the camera has to look straight down at perfect 90-degree angle. It's this tall because the stock camera has a narrow field of view, so I need this tower height just to fit the dice in the frame. Anyway, that's all for today. Thank you so much for watching.